Hey guys, welcome to video 45. We're going to continue our discussion of enhancement mode MOSFETs looking at small signal class A amplifiers. In particular, we're going to be using the common source configuration with voltage divider biasing today. The three possible amplifier configurations are the common source, source follower or common drain, and the common gate. These are equivalent to common emitter, emitter follower, and common base for the BJT. All the characteristics are similar as well, and they're summarized in this table. The common source amplifier is inverting. It's got high voltage gain, high current gain, and the highest power gain of all three configurations here. It's got a medium or moderate output resistance, similar to the common emitter amplifier for a BJT. The source follower has low output resistance. Its voltage gain is always less than 1. It's going to have high current gain, relatively high power gain, high input resistance, and the lowest output resistance of the three. And finally, the common gate configuration has the best frequency response. It's going to have relatively high voltage gain equivalent to the common source amplifier. Its current gain is always less than 1. Its power gain is relatively low. It's going to be less than the voltage gain of the amplifier. It's going to have low input resistance and a moderate output resistance. Now let's take a look at the small signal model for the enhancement mode MOSFET in the common source configuration. We can see we've got a voltage controlled current source. The drain current is given by GM, the small signal transconductance, times VGS. We've got infinite gate to source resistance, so this model is relatively simple compared to some other ones we've seen. All right, the transconductance is the derivative of drain current with respect to VGS, and for this particular device, that equation is easy to work with. We end up with GM equals 2K times VGS minus the threshold voltage. And remember, fundamentally, transconductance is the slope of the tangent line to this curve at the operating point. So for the sake of argument, let's assume we're running our MOSFET at 4 milliamps drain current. So here's our Q point. And let's determine the transconductance for that particular Q point for a 2N7000 or BS170. All right, so we've got GM equals 2 times K. K is 0.1, so that's 0.2 times VGS, 1.7 volts, minus the threshold voltage of 1.5 volts. And that gives us, let's see, 1.7 minus 1.5 is 0.2 times 0.2 is 0.04, and that would be either Siemens or Mohs. And I prefer to use Mohs because the upside down omega is much more distinctive looking. And we'd probably call this 40 millimhos. And there we go. There's our transconductance. That would be the slope of the tangent line to the curve at this operating point. Now we can also get a graphical estimate of the transconductance by sketching this tangent line. It's a little bit hard to eyeball it, but I'm going to give it a shot here. It looks like our tangent line looks pretty much like this. And we can determine GM by finding the slope of this line. That is GM equals delta ID divided by delta VGS. So in this particular case, we've got a delta ID of 15 milliamps. And our delta VGS is about 2 minus 1.6 or 0.4 volts. All right, so that gives us a transconductance of 0.015 divided by 0.4, which is, let's call that 38 millimhos, okay? Approximately 38 millimhos. And that's in pretty good agreement with what we got using the equation. So you can kind of think of this as a sanity check, and it gives you a little bit more faith in the equation we derived over here because it does match up pretty well with our graphical estimate. All right, now let's put this information together and take a look at a typical common source amplifier using voltage divider biasing. Here's our circuit. We recognize this from the previous video. We've got a voltage divider biased MOSFET. The input source is coupled through a capacitor to the gate. Our load is capacitively coupled to the drain, and we've got a bypass capacitor across the source resistor. Our DC equivalent shown over here. We covered the analysis in the last video. So all the pertinent analysis equations are shown over here, and I'll talk about these again as necessary when we do an example. So now let's go ahead and take a look at the AC equivalent circuit. All right, it's a relatively straightforward circuit. We've fully bypassed the source to ground, so what we've got is our equivalent drain resistance. R'(D) is the drain resistor in parallel with RL. The input resistance is the Thevenin resistance, RTH. And our voltage gain is negative GM times R'(D). And we can derive that really easily from this equivalent model over here, where we see that V out equals negative I sub D times R'(D). And since I sub D is GM times VGS, we can write negative GM VGS times R'(D). And of course VGS is V in, so our V out is equal to V in times negative GM times R'(D). V out over V in is voltage gain, and that's negative GM times R'(D), as we see over here. All right, now let's take all of this information and the previous information we've learned in the last video, and let's analyze a circuit. All right, so we've got a 2N7000 voltage divider biased, a 12-volt power supply, and remember for this device, K equals 0.1, and the approximate threshold voltage is 1.5 volts. Let's start by finding VTH. All right, so VTH, as usual, equals VDD times R2 over R1 plus R2, and we get, let's see, 270 divided by 1270 times 12 volts gives us a VTH of about 2.55 volts. Okay, so let's write that here, 2.55 volts. Our RTH, Thevenin resistance, is equal to R1 in parallel with R2, and that's, let's see, 1 meg, I'm just going to call that 1,000, 1 over x plus 270, 1 over x equals 1 over x, and that's about 212.6. Let's call that 213K. All right, and then we can determine our drain current using the quadratic formula, or in this case, I'm just going to call up the graphical equation plotter Desmos, and we've already got it right here. We've got our K value of 0.1 times VGS minus the threshold voltage squared, so there's our parabola. We've got 2.55 volts, that's VTH minus X divided by RS, 220 ohms. So here's our ID times RS line, and our drain current is about 3.9 milliamps. Okay, so we're going to get an IDQ of about 3.9 milliamps. The corresponding VGS we could find by doing ID times RS, or I'm just going to look at it here. We've got about 1.7 volts for VGS. Okay, so there's our Q point, 1.7 volts VGS, 3.9 milliamps for IDQ. VDS at the Q point, and notice I've appended the Q's here just because we're doing a Q point analysis. You don't have to do that. But VDSQ equals VDD minus IDQ times RD plus RS. All right, so let's see what we come up with here. IDQ was again 3.9 milliamps, so we've got 0.0039 times 1200 plus 220, and we'll subtract that from 12, or minus 12, and ignore the negative sign, and we get a VDSQ of about 6.5 volts. Okay, I'm going to write that here, 6.5 volts. Our transconductance GM is equal to 2K times VGS minus VTO, and 2K is 0.2. Our VGS is 1.7 volts minus 1.5 volts. All right, so again, that's going to be about 40 millimos. Okay, we've got 0.2 times 0.2, which is 0.04, 40 millimos. Okay. Our input resistance is equal to RTH, the Thevenin resistance, and that was 213 k ohms. Now our voltage gain, AV equals negative GM times R prime D. Let's see what we've got here. Okay, so that's 0.04 times our drain resistance, well, 1.2K in parallel with 1.2K is 600. So that gives us a voltage gain of negative 24. Our current gain, let me clear a little space here. Remember that current gain is equal to voltage gain times the input resistance over the load resistance. So our voltage gain is negative 24 times 213K divided by 1200. Let's see what we come up with here. So 213,000 divided by 1200 times 24 is 4,260. So we got negative 4,260. And our power gain, remember, is the voltage gain times the current gain. So we're going to have negative 2460 times negative 24. And that's 102,240, 102,240. Okay, 102,240. All right, pretty high current gain and power gain. Now, if we have a Vin of 50 millivolts peak, 50 sine 2 pi 1000 t, what's V out going to be? Well, V out equals AV times V in. So that's going to be 50 millivolts is 0.05 times our gain of 24 is 1.2 volts peak, and it's inverted, so we're going to express that as negative 1.2 times the rest of it, and I'll write that here, negative 1.2 sine 2 pi 1000 t volts. So there's our output voltage. All right, now as usual, I'm going to pull over a nice typeset condensed version of all this information, and let me do that now. First, let's clear out our workspace here, and here's everything we've got. Okay, so if you want to take a screenshot of this, you can. I guess I won't pull it over because it's a little bit too big to fit on the screen with the schematic. But anyway, we've got, again, an IDQ of 3.9 milliamps, VGS 1.7 volts, and we could find that I did it graphically using Desmos, but you could also do it VTH minus IDRS or IDQ over K square root plus VTO. Either way, you get the same answer. VDS is about 6.5 volts, GM 40 micro or millimos, voltage gain negative 24, Rin is 213K, and the rest of our values, and of course the output voltage. What I'd like to do next is something we haven't done for a while, and that's a DC and AC load line analysis for an amplifier. The last time we did this was, I can't even remember how many videos back, when we were looking at bipolar transistors, but we can also do the similar analysis on JFETs or MOSFETs or any other kind of transistor, or vacuum tubes for that matter. So what I want to do next is put up a quick DC and AC load line analysis for this amplifier. So let's start by just sketching our axes here. So we're going to do I sub D versus VDS, and let's put our DC load line on here. Remember, we're going to find ID in saturation, and remember, this is saturation in terms of load lines, not device parameters here. So ID sat is VDD over RD plus RS, okay? The same as we would have found for a bipolar transistor, VCC over RC plus RE. But let's see what we get here. VDD is 12 volts divided by, let's see, 1200 plus 220 is about 8.5 milliamps. Okay, so we're going to get an ID set of 8.5 milliamps, and of course, whoops, VDS in cutoff would equal VDD, which is 12 volts. Okay, so there are the limits for our DC load line. We're going to go from 12 volts to, let's, I'll just guesstimate it here, 8.5 milliamps, and hopefully our AC load line fits on here okay, but let's just draw this in. There's our DC load line. Our Q point is located at 3.9 milliamps and 6.5 volts, so we're a little more than halfway over here. Let's say this is 6.5 volts. Here's our Q point, and this corresponds to 3.9 milliamps, almost at the halfway point. All right, now let's do an AC load line for this, okay? We know for AC load lines, our ID sat is going to equal IDQ plus VDSQ divided by R prime D. All right, so IDQ is 3.9 milliamps, and I'm kind of out of room here, so let me move it down here, plus VDSQ of 6.5 volts divided by R prime D was 600 ohms. And let's see what we've got here. So 6.5 divided by 600 is about 10.8 mils plus 0.0039, which is about 14.7. Let's just call it 15 milliamps, okay? So I'd say that's about here, 15 milliamps. Remember, this is just a rough estimate. And our VDS cutoff equals VDS at the Q point plus IDQ times R prime D. All right, so what do we get here? Let's see, IDQ was 0.0039 times 600 is our R prime D, so 2.344 plus our VDSQ of 6.5 volts. So that's going to be what, 8.8 volts roughly. And that's, say, about here, 8.8 volts. And if I connect these 2 points, if I had drawn everything very nicely and proportionately, it would go right through the Q point. Of course, I just guessed at everything here, but that's roughly what our AC and DC load lines are going to look like. But I'm not going to leave you with this terrible looking stuff, okay? I've actually gone ahead and done this. And let's just go on over and take a look at the large signal AC analysis. And here's what we get, okay? So here's a nice version of everything with all the equations summarized. So our VDSQ and IDQ, our DC load line limits, and our AC load line. So we can see that based on these results, we should get a VO max of about 2.3 volts. That's the distance from VDSQ to VDS cutoff, and a VO min of negative VDSQ, so negative 6.5 volts. We're going to have asymmetrical clipping. All right, and to verify all of this, I did build the circuit and tried it with a few different 2N7000s, and I'm going to show you those results next. Okay, now what we've got is a table where I'm comparing our theoretical values with the measured values I averaged out for a couple different transistors. So we can see the drain current is in good agreement, VGS is right on the money, VDS is pretty good too, and our actual voltage gain is a little bit lower than the theoretically predicted value, but that's to be expected. Normally, an amplifier is not going to be quite as good as the theoretical value in terms of voltage gain, because we made some approximations here to keep things simple. Our large signal limits are in pretty good agreement with our theoretical analysis. And now if we come over and look at this first scope trace, I started with an input voltage of 100 millivolts peak to peak roughly, and that gave us an output of about 1.86 volts peak to peak. Taking the ratio 1.86 divided by 0.104 gives us the gain of 18, and of course it's inverted. All right, now if we come over here to the next scope capture, I increased V into 250 millivolts peak to peak. It wasn't enough to cause clipping, but we do have some very noticeable distortion. Note that positive going outputs are not amplified as much as the negative going outputs. That is, the gain to negative going input signals is smaller than the gain to positive going input signals. All right, this kind of distortion would be pretty undesirable for hi-fi applications, but if we're building an effect circuit, say a distortion effect or something, this is not a bad thing to have. This also happens with bipolar transistors and JFETs, and in a future video we're going to really do a deep dive into this kind of distortion and compare all these devices. But for right now, it's just something to be aware of. We do get asymmetrical gain for positive and negative going inputs. All right, and finally over here on this third scope capture, I applied 1 volt peak to peak on the input, which drove the amplifier into saturation. And we can see we reached a maximum peak output of about 3 volts and a maximum negative value of -5 volts. And those are our clipping values that we would get from our AC load line, and we've got, pretty good agreement with the theory. Now let's take a second and talk about what happens if we don't have source bypassing. Here's our amplifier. I've removed the source bypass cap, and here is our AC equivalent circuit. Notice that R'(D) is the same, Rn is still RTH, but our voltage gain is now negative GM times R'(D) over 1 plus GM times R'(S), where R'(S) is just the source resistor in the AC equivalent circuit. Now, I'm not going to derive this equation in this video. It's a bit long and tedious. I'm going to save that for the next video where we talk about drain feedback biasing with the common source amplifier. So get ready for that one. It's going to be a very mathematical video. But for right now, we'll just take this equation as given, and notice that if I do fully bypass RS, the denominator just becomes 1, and we get the original gain equation that we talked about earlier. Now, as far as bypassing the source goes, we've got some options. We can fully bypass it, which gives us R prime S equals 0. We can have no bypassing, where R prime S equals RS. And we have two different partial bypassing options, splitting RS into two parts, or putting a capacitor in parallel with some resistance. And it gives us these two other options for partial bypassing. All right, and I'm going to leave you with a homework problem again. This time we've got a 2N7000 biased up as a Class A amplifier powered by a 9-volt battery, and we're using power switching via the input jack. We've seen that before, and all I want you to do is determine the usual amplifier parameters, assuming our pots are maxed out so we get maximum output voltage. All right, and as I said, the next video we're going to take a look at drain feedback biasing and the common source amplifier, and we're going to derive the voltage gain equation for a non-zero source resistance. Okay, so I'll see you guys next time around.